In the third column, you will have, what you are doing is you have to multiply qn into qn plus 1 by qn minus 1 and then add qn plus 1. And you have to drop the last term in the second column. So you have the third column like this: q1, q2, q3, q4, and there is a large term that is qn minus 1 into qn plus 1 plus qn plus 1, and the last term in the third column is qn into qn plus 1 plus 1. So if you repeat the process, finally you will have two numbers which are denoted as hn and gn. This hn and gn, that is hn by gn, would be a successive approximation, is an approximation to h by g. So for example, consider g as 576 and h equals 210389, which are the Gunakara and Haraka of the sun. When I say Gunakara and Haraka of the sun, it means it is the ratio of the number of revolutions of the sun in a Mahayuga divided by number of civil days in a Mahayuga, or vice versa. So dividing h by g, we get h by g equals 210389 by 576 equals 365 plus 149 by 576. Here the quotient is, first quotient is 365 and the remainder is 149. We once again divide 576 by 149 to get 3 as the quotient and 129 as the remainder. Okay. So now repeating the process of division, we have the Valliphalas or the quotients, successive quotients are 365, 3, 1, 6 and 2. It may be noted that we have terminated the process. You can terminate the process at any point, okay, where you feel that the remainder is minimum. So here we have terminated the process at q5 equals 2, and in that case r5 is 2. Placing these Valliphalas one below the other with 1 at the bottom, we have 365, 3, 1, 6, 2, 1. So in the next column, we'll have 365, 3, 1, and 6 into 2, you have to, that is 12, plus 1, if you do, you have 13. Would be the term in the same row of 6. Okay. So if you repeat the process, we have these results. We'll have 5 columns. In the fifth column, we'll have only 2 numbers, 21185 and 58 respectively. Here, 58 and 21185 are the alpa. They are known as alpa gunakara and alpahara. The large numbers which we have taken, 576 and 210389, they are known as mahagunakaras and mahaharas. Here 58 and 21185 are alpa gunakara and alpahara of the sun respectively. Thus we have 58 by 21185 is an approximation to 5076 by 210389, which is correct to more than 4 decimal places if you just compute this. So that's what we have now discussed the Valluppasamhara method 1. Now the Valluppasamhara method 2, given in Karana Paddhati, in the 6th verse of Karana Paddhati, it goes like this. Anyonya-hrita bhajya-haraka-phalam sarvam tvadhodhonyaset ekatradya phalena hinam aparatraikam dvayaschopari kuryat Valluppasamhritim hyuparitaha purva pranasham vina tyajyam tat prathamordhvagam haraguna shishtascha svechaya. So there are some differences between Valluppasamhara method 1 and method 2. Valluppasamhara method 1, you only get one successive approximation, but in method 2, you will get all successive approximations that are possible. Okay, possible successive approximations to that ratio of big, larger multiplier and divisor. So the translation goes like this: the results obtained by dividing guna and hara mutually. Here also you have to perform mutual division of the multiplier and the divisor, and successive results have to be noted down. So the results obtained by dividing guna and hara mutually by each other have to be kept one below the other at one place. Place the same result one below the other at another place, because you have to record these two at two different, simultaneously you need to do operations at two different places, because you are going to get in one process in first if you perform the process at one place, you will get the successive multipliers. In other place, you will get the successive divisors independently. So in the previous method, you got one divisor and one multiplier at a time, but here you will get them separately. So so you have to keep this successive quotients one below the other, okay, at one place, at the two places. So placing one, and you have to place one above in both places. In the previous algorithm, we have placed the one below the at the bottommost position. Here you have to place at the top. Okay. Then Valyupasamhara be done. Valyupasamhara means the process that you have to multiply the penultimate and the previous one terms, and you have to add or subtract. You have to add it to the last result. Okay. So here you need not, and in the previous place you have deleted the last term. Here you should not delete the last term. So however, the first from the first column has to be dropped. So we will see that how it works. So Q1, Q2, Q3, Qn are the successive quotients that we have obtained. You have to place one below, one above the Q1, okay? And then what you need to do? You need to multiply the second term. Here now, as far as this column is concerned, the first term is 1, second term is Q1, third term is Q2. Now in the second step, you need to multiply second term with the third term and add the first term. So in the second column, the first term would be 1 only, second term would be Q1, third term would be Q1 into Q2 plus 1, and from fourth onwards up to nth term, you have Qn to Qn, Q3 to Qn. So in the third term, in the third column, you have one Q1, Q1 into Q2 plus 1, and fourth term would be Q1 into Q2 plus 1 into Q3 plus Q1, okay? So you have to repeat the process. In the first algorithm, method 1, you had started from bottom. Here you have to start it from you have to do this Valyusamhara, means the multiply the second term with the penultimate term and then add the first or the last term, okay? So there is a product that has to be added to the one of the terms. Here you have started it from the top. There you had done it for the bottom. So finally, so you will obtain at the nth column, if you repeat the process, nth column would be 1 Q1 into Q2 plus 1, etc., and Hn minus 1 into Qn plus Hn minus 2. So all these terms would give you the successive divisors, or H represents hara, the successive divisors or the successive haras, okay? And here Q1, the second term should be the first divisor, third term should be the second divisor, third term is the second divisor, because here as per the procedure, one has to be dropped, okay? One has to be deleted, okay? So by doing this, you will get the successive multipliers, okay? And similarly, you have to do the same procedure or the same process in the case of in order to obtain the gunakaras, successive multipliers. Only the difference is you have to place one above the quotients as done before, but you need not, one should not consider the first quotient. So without first quotient, you have to place all other quotients, that is from Q2 to Qn, you have to place one below the other, and then keep one above, and repeat, do the Valyupasamhara or continue the process. So you will get 1 as the first term, Q2 as the second term, Q2 into Q3 plus 1 as the third term. All those terms become the successive multipliers of that ratio h by g. So G1 equals 1, G2 equals Q2, G3 equals Q2 into Q1 into Q2, Q3 plus 1, and so on. Here, Q1 does not come into picture because you should not consider Q1 at all. In the previous case, you have to consider Q1 and you have to place 1 above Q1, but you need to delete 1 at the end, okay? So that Q1 becomes the first divisor. Here 1 becomes the first multiplier and Q2 becomes the second multiplier. So here this is an example. Here you can see there are two very large numbers which are given in blue color. So these large numbers are nothing but it's the second column, that is GI alpha gunakaras column. The last entry which is in blue is nothing but the number of revolutions of the moon's anomaly, which is known as Bandha Kendra, and moon's anomaly takes these many number of revolutions in these many number of days. HI, there are two blue two numbers which are colored in blue. In the first column, it gives the number of days, and the second column it gives the number of revolutions. So moon's anomaly takes these many number of revolutions in these many number of days. And if you do the Valupasamhara, you will get the successive approximations for this, which means you have 27-1, 28-1, that is 1 by 27, or 2 by 55, or 9 by 248. They are nothing but the ratio of number of revolutions of the moon's anomaly around the earth to the number of civil days. Okay, or in other words, you can say moon takes nine anomalistic revolutions in 248 days approximately, because these are all approximations. Now, what do I mean by this moon's anomaly? See here you have Earth and moon is revolving. You have moon here. Moon is revolving around the Earth. Okay, and you can see a direction which is known as U, that is moon's apogee. So when moon coincides with U, which means moon has the slowest motion. Think that moon starts its motion at U at any close to any in a day, close to the sunrise of that day. Moon takes the duration for the moon to come back to U, because U is also this moon's apogee. That's the point at which moon has the slowest motion, also moves in an opposite direction. Okay, so the duration or the time period taken by moon to come back to its apogee is known as the anomalistic period. Okay, so when suppose it starts its motion at the time of sunrise on any specific day, it takes approximately 9 revolutions to come back to the same position and is close to the sunrise. Okay, and for taking that 9 revolutions, moon takes 248 days. Okay, moon takes 248 days. So because this is the number of anomalistic revolutions close to the sunrise is an important aspect as far as Vakya school of astronomy is concerned, Vakya system is concerned. Because Vakya system, we will be talking about briefly later about Vakya system. So in Vakya system, Vakya is literally, it means sentence, in which some of the astronomical parameters are encoded in that. There is a number which is associated with each sentence, and these numbers are encoded using Katapayati system of numeration. And you have set of Vakyas. We will briefly see how Vakyas look like, and using Vakyas, the computations become very easy to compute moon's longitude or any other astronomical parameter. So in order to use the Vakya system, there is an important concept which comes is the khanda. So in order to understand what is known as khanda, we need to know what is known as ahargana. Ahargana is nothing but ahaha means the day, gana is group of days from the epoch. Epoch is in Siddhantic astronomy, epoch is generally considered as the beginning of Kali Yuga, that is February 18, 3102 BC. And here you can see desired day. Desired day is the day in which we are the computed or the parameters, astronomical parameters such as the longitudes of the planets are desired. So the duration between these two instants or these 2 days in number of days is known as ahargana, that is group of civil days between epoch and desired day. Khanda literally means is the part. So the part of this ahargana is known as khanda in this context. So you have to choose the khanda appropriately so that if you suppose for example the khanda is a day in which moon coincides with its apogee at the sunrise, or in other words the conjunction of moon and its apogee taking place at the sunrise on the day of khanda, and or that day is referred to as khanda, as the khanda. So mathematically it's an interesting problem. If you know the ahargana, how will you fix the khanda? How to compute the khanda? That's an important problem which has been mentioned in which has been addressed as far as Vakya system is concerned. But the Vakya system or the Vakya text, they just give the khandas. Okay, okay, this is the 160420 is the khanda as per Vakya Karna, for example. So that's not the exact number. They just provide the number as khanda, but they don't talk about the how to obtain the khanda from ahargana. If you know the ahargana, how can you obtain the khanda nearest to that ahargana? So that is not addressed in the Vakya system, whereas the text Karana Paddhati gives an interesting algorithm to obtain the khanda if you know the ahargana, or obtain the khanda closest to the ahargana A. So here you can see in the equation below, A is nothing but the ahargana. So the khanda or and it could be called as contemporary epoch, which means you are actually shifting this epoch which is February 18, 3102 BC, that's the epoch in Siddhanta Shiromani, which you are actually shifting that to the nearest to a day which is closest to the ahargana. So this is how the algorithm goes. Devendra Sharmekya Dinendu Tunga Bhedardha Yukteshta Dinendu Kendrat Niptikritat Kendra Hareshvabhishtena Hatya Nanarti Pareira Vaptaha Abhishtaharordhva Harena Hatva Urvodita Abhishta Harena Hratva Tatradhikonam Yuganat Visodhyam Arauja Yugmatva Vashakramena Shishtam Shashankodita Vakya Khandaha. So Shishtam is the remainder, Shashanka means the moon, Udita Vakya Khandaha means the khanda in terms of Vakya. So he is actually talking to get some remainder. What is that remainder? So you need to first find the theta 0 minus theta m. Theta 0 is the longitude of the moon, theta m is the longitude of its apogee at the day of ahargana. With respect to ahargana A, you need to find theta 0 minus theta m. Then you need to find theta 0 minus theta m for 303 days, and that has to be half, and that has to be multiplied by hi. Hi is the so if you go back, this is the hi that is used. So you can take any values in this in the first column, and gi is the second column. Okay, so gi is not required here. So hi, if you take, say for example, if you take hi as 12372, gi would be 303. 12372. Hi minus would be 3031. So here you have freedom to choose any hi. If you choose hi as 12372, then hi minus 1 is obviously 3031. Okay, you have to multiply this result theta 0 minus theta m a by plus theta 0 minus theta m for 303 by 2 by hi, and divide it by 21600. Take the integer part of it, then multiply it by hi minus 1, then again divide it by hi, and take the remainder of this quantity. And if you get the remainder, suppose Ri is the remainder that is obtained, then Ki, the khanda, or it is referred to as khanda dina because it is in days. The unit is in days. You have to subtract this Ri from A when hi is odd. Okay, for example, if you take hi as 12372, then 1, 2, 3, 4, 5, 6. 12372 is an I is even here. I is even. So for even hi means for even I is actually you need to find hi minus Ri, and that hi minus Ri has to be subtracted from A. So if you do so, you will get the khanda dina. So Karana Paddhati explicitly gives this expression of the algorithm using these two verses. That is, it comes in third chapter of Karana Paddhati, the second and third verses. If we try to analyze this algorithm, or if you try to find the rationale for this algorithm, it's clear that this is the rationale. I'm not planning to go through the rationale. You can see that Padmanabha Somayaji, who is the author of Karana Paddhati, it seems he has used the properties of continued fraction, because the relation between successive convergence gi into hi minus 1 minus hi into gi minus 1 equals minus 1 all raised to I plus 1, and gi x dash minus hi y dash equals 1 for odd i's, and x dash equals hi minus 1 for x dash would be hi minus 1 for odd i's, and x dash would be hi minus 1 for even i's. So he has used the properties of continued fraction, without which it is not possible to construct such an algorithm. And we have proved in we have published this book on Karana Paddhati, and we have proved this in that book. And so you need to have the clear understanding of continued fraction and its properties in order to arrive at the algorithm for finding the khandas. Okay, so that I just wanted to emphasize there. So not only this, so this is one instance where the Padmanabha Somayaji, the author of Karana Paddhati, uses the continued fraction and its properties to solve an astronomical problem. Here the problem is to find the khanda. Okay, so there are several such algorithms or such cases which are present in Karana Paddhati's third, fourth, and fifth chapters. Okay, here we have only shown only one such case. Okay, so this is about the application of continued fraction which is used in Karana Paddhati. And though the technique Valyupasamhara has been used in the solution of indeterminate equation, which is known as Kuttakara or Kuttaka method, by Aryabhatta or Brahmagupta and so on, they are not explicitly mentioned in any of the texts. So implicitly, it is the Valyupasamhara which is used to solve the indeterminate equation. But for the first time, Karana Paddhati, the Paduna Somayaji, who is the author of Karana Paddhati, gives an explicit technique in an explicit way to find the successive approximations to a ratio of two large integers. And Karana Paddhati has been composed during 1532 CE. So now, currently we are working on another text called Dritkarana, which is an interesting text. Karana Paddhati is purely in Sanskrit in the form of verses. Similarly, Dritkarana is also in the form of verses, but they are sort of in a language, composed in a language known as Manipravalam. Manipravalam is a language which is a mixture of Sanskrit and Malayalam. Okay, so in 1532, Karana Paddhati gives two different techniques to find successive approximations of a ratio. In 1606, this Dritkarana, the text Dritkarana, composed during 1606 CE, about half a century later, develops a little further and gives something known as nearest integer continued fraction. We have used the term semi-regular, but it is actually nearest integer continued fraction technique. And it is composed in Manipravalam language. So it goes like this: Anyonya haranam cheyu bhudinam paryayangalum phalangale kramattala dhodho vechatu kondatha. So the technique is almost same as compared to the second method of Karana Paddhati. Except one part. So here Anyonya haranam means you have to mutually divide. Bhudina and Paryaya here refers to the number of revolutions. Bhudina refers to the number of civil days. Phalangale means the results. Kramattal, adhodho, kramattalang adhodho means one has to keep these results one below the other. Then he says dhanarnatmakangalayulla gunaharan vartuga. Obtain the successive multipliers and divisors which are of the nature of dhana and rana. Dhana means which are additive in nature or subtractive in nature, or the negative or the positive kind of quantities. Now, here is the twist. So, in the fourth line, he says, Swapurva gunanignaste tatpurvena cha sanyuta. So, this is similar to the previous method. Gunaharashcha jayante rupam adigunam. Rupam again, the one which would be the first multiplier. Then, in the eighth line, if you see, paraspara hritau shesham yada tu ardhadikam bhavet. When you multiply them mutually, so the process is actually the mutual division of successive results, right? So paraspara hrita is mutual division of successive results. When while performing the mutual division of successive results or the successive quotients, the shesham is the remainder. When shesha or the remainder, if yada means if, ardhadikam bhavet, if it becomes more than half of the previous remainder that is implicit here, if it becomes more than half of the previous remainder, then you need to add rupam. Rupam phale yogyam. Yogyam means you need to add to the result. So whatever the next quotient that you will be obtaining, you need to add one to that next result. Okay. Then shesham harat. Then you need to continue the procedure or the process as done before. Okay. For example, the same way. So if you have one Q1, Q2, Q3, you have to place one below the other, and at the top you have to place one. And if Ri is less than Ri minus 1 by 2, then Qa and Ri remain as it epsilon I plus 1 becomes 1. Here you have epsilon, we have given epsilon i's here, and however if Ri is greater than Ri minus 1 by 2, then Qa has to be QA has to be converted to QI plus 1. So this plus 1 is not subscript. It has to be plus 1 is you have to add plus 1 to QI. So QA has to be transformed to QI plus 1. Okay, and Ri has to be transformed to Ri minus 1 minus Ri. Okay, and then in that case EI plus 1 becomes minus 1. So from next step onwards, okay, having done this, you will obtain QI as QI plus 1 and Ri as Ri minus 1 minus Ri. You have to continue the process. So again, we have taken we have computed or found the successive approximations for the ratio 2174168448881 by 5990826777500, and you have this 24 successive approximations, and this is the first one is actually the Karna Paddhati method, the normal method, the regular continued fraction method, and the second table which gives the nearest integer continued fraction method, where you have the number of terms that you obtain is lesser than or the number of successive coefficients that are obtained of a ratio are lesser than the number of ratios that are obtained in the Karna Paddhati method. And here actually what happens is it approximates to the nearest integer. That's why it's called nearest integer continued fraction method. Here we have compared the successive divisors Hi and multipliers Gi obtained by the regular continued fraction method of Karna Paddhati and the semi-regular or the nearest continued fraction method of Drikkarana. So in this here I take an opportunity to acknowledge my collaborators for Karna Paddhati, Professor K. Ram Subramanian, Professor M. Shriram, who is here, and Professor M. D. Srinivas. And the Drikkarana we have been doing from past couple of years, and the collaborator is Professor M. Shriram. I would like to thank Professor M. Shriram for this as well. Thank you very much. Thank you.
Yeah. Thank you, sir. Thank you. Thank you for your enlightening and entertaining lecture. And he has you sir explained the beautifully the methods of Velupus Mahara's astronomical, which are from astronomical data as Karna Paddhati. Sir has presented the method of approximate fractions. He has explained the Velupus Mahara method 1 and method 2 with some examples. He has also discussed semi-regular continued fraction in the Karna. I hope all the participants must be benefited from it and have enjoyed your lecture, sir. And thank you again for your contribution. Now the session is open for any queries. Is there any query, any doubt if anyone want to discuss anything?
Yeah, just one remark.
Yes,
sir. Yeah.
Yes,
no, actually, we're talking about the Valli Upasamhara method. It is nothing. It's very close to Kuttaka. Same kind of procedure is used. The Professor Katre was doing this for the previous lectures. So various columns and all that, right? One column after the other. Then how to go to from one column to the next. You see, you multiply, add something to the previous one, and then multiply and go to the next entry like that, right? So that is the Kuttaka method. But there it is solving. See, solving for x and y. Ax plus c is equal to by. Here you are not solving. You are trying to approximate any ratio. At some suitable stage, you truncate and you get the convergence. So successive convergence, how they are getting, we are getting how they are related. So that is what is Valli Upasamhara of Pudumana Somayaji. and somewhat modified by Drukkarana, author of Drukkarana. We don't know who is the Drukkarana author. Most maybe Jyeshtadeva. So to get the nearest integer.
Okay, sir. Thank you, sir.
Yeah,
Any
thank you,
other-
Professor Shriram, for that comment. Yeah.
Yeah.
So, anyone else, if you want to ask anything? Okay. Okay. Thank you, sir. Thank you again for your contribution. Now, this was the last lecture of this session. Now, we will meet again tomorrow at 11 a.m. for the next session. Till then, have a nice time.
Okay, thank you,
Thank you.
thank you, thank you, Dr. Pai.
Yeah, thank you, Professor Dani. Yeah.
Tomorrow we will meet again. And please, all the participants, please join well before time so that we can start timely. Okay, so thank you everyone.